Alright, so we're beginning our last section of this class where we're going to look at galaxies, the Big Bang, and basically how it all began. So we start off by looking at our own Milky Way galaxy, simply because, of course, we know the most about it. So this is what the Milky Way galaxy looks like to you. You probably don't get this view unless you're out in a pretty remote area where the light pollution doesn't obscure the view. And you might have seen this band of milky white across the sky. When you look at this, what you're actually seeing is you're looking sort of through the galaxy, like in an edge-on way, like you're looking through the disk, through the most populated area of the galaxy. When you look further up from top to bottom, you're looking, above the disk and below the disk, and that's why there's not as many stars. So when you look through the thickest part of the Milky Way, you see all these stars, and this sort of illuminated area is the sign of dust and gas, which is sort of scattered by the light. And then there are regions that are sort of dark, that a lot of the stars are obscured. This is where the gas is so dense that it blocks a lot of stars from your view. And remember from the very first day of class that we are not at the center of the Milky Way galaxy, but about 28,000 light years out from the edge of the galaxy. This is what I told you about earlier, the dusty gas that obscures stars from your view. We call it the interstellar medium, and it is this medium where the material is available to form new stars. So let's talk about some of the early beliefs of our galaxy. In the late 1700s, William and Carolyn Herschel counted stars in the sky in all directions. And what they did is, when they did this, similar to that very first picture that I showed you, they sort of found that there was more population or more density of stars in certain directions than others, which led them to conclude and correctly that the Milky Way was disc-shaped, so that it was wider, more wide than it was thick. In the early 1900s, work done by Kapteyn did some more sophisticated star counting, and his results led him to believe that we were centrally located in the galaxy. Basically, what he was doing was he was sort of looking in different directions and counting how many stars. And he knew, and what he found was sort of the same result in all directions in terms of around the disk of the Milky Way, and that's why he was concluding that we were at the center. He knew that his results would be incorrect if something was obscuring the stars from his view, but he didn't realize that this material was there. So this is a good example of sort of following this scientific method and coming in up with an incorrect result, but that's okay. I mean, he sort of did what he could, and his results sort of led to sort of the present understanding, when I say present, in his time, of where we were in the Milky Way. At the same time, Harlow Shapley was counting globular clusters. If you remember, those were little found around the bulge, the central bulge of the Milky Way, and those are little groups of stars. So Shapley found that they were actually not symmetrically surrounding us, but actually symmetrically surrounding another location in the Milky Way, and he correctly surmised that it made sense if they were sort of centered around the very center of the Milky Way. And so eventually this helped people realize, and also the recognition of the interstellar medium made astronomers realize that Kapteyn came up with the incorrect result because there were some stars obscured from his view affecting his results, and so that we realized eventually that we were not in the center of the Milky Way, but actually a little bit out from there. And so this picture should look familiar to you. Looking at the Milky Way from the side, you see where the sun is, you see the bulge, and then these are the globular clusters that Shapley had looked at. And you notice that they are sort of symmetrically distributed around the central bulge of the Milky Way. This is the way the Milky Way looks. If we could come out of the Milky Way and look at it, this is what we believe it would look like. So when we look at the Milky Way, there are basically two populations of stars, and these are pretty important. The two populations of stars are going to be stars that are found in what we call the halo, and that's the larger area that surrounds the entire galaxy. That's also where the globular clusters are found. And then there's also the disk stars that are found within the main disk of the Milky Way. The stars in the disk tend to just orbit around the center of the galaxy. They may deviate and go above the disk and below it. What happens is as they go up above, the gravity of the stars in the disk will pull them back down, and then they might sort of overcompensate and go below, and they get pulled up and so on. So they'll sort of do a little up and down motion as they go around the center of the galaxy, but they're all moving in the same direction. If we look at the stars in the bulge and the halo, the same isn't true. They're sort of coming at all different directions, and of course are not at all constrained to the disk of the Milky Way. And so this is just a summary, again, a picture looking at this. And besides the fact that they travel very differently, we find that their different orbits is additional evidence that the origin of these two groups of stars is different. They actually are two sort of groups or categories of stars found within the Milky Way galaxy. That would be the halo stars and the disk stars. We'll come back to that in a minute, but first of all, we're also going to talk about something that's pretty important for the rest of the class. This is another picture that you should recognize from the very beginning of class when we talked about how the sun orbits the center of the Milky Way. And it's because it's about 28,000 light years away from the center of the Milky Way, it has a very long orbit. It takes about 230 million years for the sun to orbit the center of the Milky Way once. Now, if you remember, when we talked about Kepler's laws, Kepler's third law relates the distance from the central point and the amount of time that it takes to orbit. Kepler's third law really applies to any time an object is orbiting under the influence of gravity. And what some of you didn't quite get, and I saw evidence of this in the Jupiter's moons exercise, is it is the mass of the material that the object is orbiting around that plays a role in Kepler's third law. It doesn't actually depend on the mass of the object that's doing the orbiting. So by looking at what we know about the distance of the sun and its orbit, we can actually infer or deduce the amount of mass within its orbit, because all of this mass within the orbit of the sun is exerting its gravitational force on the sun and influencing its orbit. And it tells us that there's about 10 to the 11 of mass of the sun. So it's like having 10 to the 11 suns are within this orbit. And this has to do with, this mass also has to do with the distance and then also the speed of the orbit. And this actually ends up leading to something rather interesting. If we were to consider the amount of material that we can see, the amount of stars that we can see at different areas of the Milky Way, we would expect that the speed of rotation would drop off, relatively quickly as we move away from the center of the Milky Way. So this is what we would expect if only the material, only the stars that were visible to us were influencing the orbit of the stars that are orbiting the center of the Milky Way. However, The actual curve, when astronomers do collect their data, looks like this. So there's a difference between perhaps what we might expect, which is this bottom line, and what we observe, which is the top line. And basically what this is this is the first piece of evidence for what we call dark matter. Because the fact that the velocities of stars orbiting the center of the Milky Way do not drop off as expected tells us that there is mass influencing the orbit of these stars. However, we cannot see this mass, and that is where the term dark matter comes from. And so we're going to talk a fair amount about dark matter for the rest of the class, and so it's pretty important that you understand that concept. So again, to remind you, the dark matter is sort of, it's implied from what we observe about the motion of stars as they orbit the center of the Milky Way. And it seems that their orbit tells us that there is more mass present than we can see with our eyes, more than we can see when we're looking at all the stars. And that's what the name dark matter comes from. In our Milky Way, there is star formation going on, and it's called the star-gas-star cycle. I actually went over this in a separate video, so I'm not going to spend a lot of time talking about that, and we're going to kind of go through these slides relatively quickly. You can both read and watch the other video to get that material. So we're going to talk about from the Earth. Okay, so that cycle, which I did go through pretty quickly, but as I said, it is material available to you in a separate video. Where do the stars form in our galaxy? Well, it has to be in these clouds of material that are dense, and where they're dense enough so that the star formation can start. We find that stars are forming in what we call the ionization nebulae. Nebula, again, is a term used a lot in astronomy that refers to anything that doesn't have a definite shape. So it's usually a glob of gas and dust. The ionization is happening because stars are forming and they're giving off a lot of heat, causing gases in this area to be ionized. We also see reflection nebula because the light given off from these new stars is being sort of reflected off the dust and gas as well. When we look at our Milky Way, notice that we don't see any ionization nebulae or no blue stars in the halo. However, we see a lot of this in the disk of the Milky Way, which tells us that it's the disk of the Milky Way where the star formation is taking place. And we'll continue looking at that in the next video.